The story of 3I/Atlas, an interstellar visitor now moving through the inner solar system, begins with its emergence from behind the Sun after perihelion, a moment that has stirred excitement, speculation, and confusion in equal measure. When the comet slipped behind the Sun on October 29, 2025, fading to around magnitude 9.5, ground-based telescopes were effectively blinded by geometry alone, leaving Earth-based observers unable to track it for several days. But spacecraft positioned far from Earth, including NASA's Punch mission, continued monitoring the region. By stacking late October images taken close to the solar limb, Punch extracted a faint but steady signal and confirmed that the comet remained at magnitude 9.5, far too dim for the naked eye and only barely reachable for mid-sized amateur telescopes under ideal conditions. Spacecraft imaging circumvents many of the limitations that plague ground observations, such as atmospheric haze and daylight scattering, allowing them to view objects close to the Sun that would otherwise be lost in glare. Even so, these images were noisy, washed in solar background, and provided no crisp detail, no dramatic tail, no defined jets, only a compact, fuzzy glow against the Sun's bright backdrop. As the comet rounded the Sun and early November began, the elongation angle, the apparent separation between the Sun and comet, increased gradually. This widening is crucial because it lifts the comet out of the Sun's blinding glare, slowly bringing it back within the reach of terrestrial telescopes. Professional and amateur astronomers alike have waited eagerly for the first uncontaminated ground-based frames, though early attempts remain hindered by dawn brightness and atmospheric interference. Every new observation still carries large caveats. Brightness measurements are approximate, the coma remains unresolved, and any hint of a tail is barely distinguishable from the surrounding haze. But the essential fact stands: despite passing behind the Sun, 3I/Atlas did not disintegrate or vanish. It endured perihelion and is steadily becoming clearer as it moves into a more favorable observational geometry, giving scientists a growing dataset to refine its orbit and physical characteristics. Tracking its motion after perihelion revealed a small but persistent offset between predicted and observed positions, primarily measured as a right ascension shift of only a few arcseconds. To the unfamiliar, such mismatches might seem like evidence of something exotic, but astronomers recognize them as textbook behavior for active comets. These differences arise because outgassing, jets of gas erupting from the surface as sunlight warms volatile ices, acts like tiny thrusters, imparting slight non-gravitational accelerations. JPL models include standard parameters known as A1 and A2 to quantify these accelerations. A1 corresponds to acceleration along the Sun-comet line, while A2 refers to sideways acceleration within the orbital plane. For 3I/Atlas, recent JPL solutions place A1 at approximately 1.7 times 10 AU/day superscript 2 and A2 near 7 times 10 AU/day superscript 2, values firmly within the normal range for moderately active comets elsewhere in the solar system. When these parameters are incorporated into orbital solutions using the Marsden formalism, a widely accepted method in comet dynamics, the residual errors between observed and calculated positions shrink to within expected noise levels. In other words, nothing about the comet's trajectory requires invoking alien engines, artificial technology, or anything beyond well-understood outgassing physics. As one JPL scientist put it, this is standard cometary behavior occurring in an environment energized by an unusually active solar wind, not a sign of artificial propulsion. For comet specialists, these numerical values are familiar territory. The interest lies not in anomalies, but in how typical cometary processes behave under the extreme plasma conditions imposed by an interstellar comet's high-speed passage through the inner solar system. Much of the comet's behavior is shaped by the plasma environment around it. Plasma processes dominate the space surrounding every active comet, and 3I/Atlas is no exception. 5 major plasma interactions define the physics at play. First, photoionization occurs when ultraviolet sunlight strips electrons from neutral atoms, streaming off the nucleus, creating ions that interact with magnetic fields. Next comes charge exchange, where solar wind ions collide with neutral atoms in the coma, swapping electrons and producing fresh ions that glow in X-ray wavelengths. A third process, mass loading, takes place when these new ions enter the solar wind and begin to slow and divert the flow, altering the structure of the solar wind itself. The fourth is the bow shock, a wave-like front formed where the solar wind must abruptly decelerate as it encounters the expanding atmosphere surrounding the comet. The fifth is the ionopause, or cometopause, the boundary where ions from the comet push back against the solar wind strongly enough to create a protective bubble. All these processes operate simultaneously around 3I/Atlas, shaping its brightness, coma structure, and even subtle aspects of its trajectory. Dust grains also play a surprisingly dynamic role. As the comet's dust flows through the inner solar system, grains accumulate electric charge under constant bombardment by high-energy particles and ultraviolet radiation. When the electrical stress exceeds what the grain can withstand, it undergoes a micro-explosion, fragmenting into smaller pieces with much larger surface area to mass ratios. These fragments respond more strongly to solar radiation pressure and magnetic forces, leading to sudden apparent changes in the comet's brightness, shape, or motion. Rosetta observed such micro-explosive fragmentation at Comet 67P in 2015, where sudden dust events dramatically reshaped the coma in less than a day. Similar processes almost certainly contribute to the subtle variations seen in early images of 3I/Atlas. One of the most important analogies comes from a dramatic event observed by the Rosetta spacecraft. In July 2015, a coronal mass ejection, CME, from the sun-struck Comet 67P. Rosetta's magnetometer recorded magnetic field values jumping from roughly 50 nanotesla to nearly 300 nanotesla within hours, a six-fold surge that mission engineers described as a magnetic wall. This sudden spike demonstrated how violently a comet's plasma cocoon can react to a solar storm. During the event, Rosetta's instruments observed abrupt shifts in ion flows, reconfigurations of the dust environment, and large-scale movements of the plasma boundary, all occurring on timescales of minutes to hours. ESA scientists later summarized the lessons simply. A CME impact can wrap a comet in a dense, highly energized plasma shell, dramatically altering its magnetic and dust environment. This precedent matters for interpreting 3I/Atlas because on October 21, 2025, the Sun launched a powerful CME from active region 4246, just as the comet approached perihelion. GOES 19 coronagraph imagery captured the eruption from the Sun's far side. Although it missed Earth, its trajectory and expansion made it highly plausible that the CME's shock wave intersected 3I/Atlas. Traveling at estimated speeds above 1,000 kilometers per second, such a CME would reach the comet's heliocentric distance within 2 to 3 days, placing the probable interaction window between October 23rd and 26th, precisely when the comet was rounding the Sun's far side. While no spacecraft was present to measure in situ plasma or magnetic fields at the comet, models of CME propagation suggest a reasonable chance of interaction. If a CME did strike the comet, it could have temporarily intensified the local magnetic field, compressed the plasma environment, and disrupted or truncated the ion tail. Similar disruptions, including tail disconnection events, have been documented repeatedly in comets experiencing solar storms. Although unconfirmed, the October 21st CME remains the leading candidate for any sudden changes in the comet's behavior during this period. Reconstructing the comet's post-perihelion plasma environment requires synthesizing incomplete datasets. With no spacecraft in the vicinity, scientists rely on solar wind propagation models, coronagraph images, and distant remote sensing data from spacecraft like Stereo and Punch. These tools offer partial views of the comet's condition, but cannot fully resolve its coma or tail. Early reports indicate a short, faint, almost stunted tail, barely distinguishable from the coma. This could reflect weak dust production, strong solar wind stripping, or a tail disrupted by CME interaction. The nucleus's size is also uncertain. Current estimates range from a few hundred meters to perhaps a kilometer across, but no direct silhouette or rotational light curve has been captured. Every parameter carries broad uncertainty, shaped more by the limitations of available observations than by the comet's intrinsic properties. Models developed by JPL and other research teams borrow heavily from better-studied analogs like 67P, making use of prior knowledge about plasma